Today we will study Biot Savarts Law. Just as Coulomb's law relates the electric fields to the point charges, the Biot Savarts Law relates the magnetic fields to the currents. In Coulomb's law, we studied the electric fields due to various charge distributions. So, if dq is a small charge element of a charge distribution, then the electric field produced by this particular charge element at point P, or in other words, the contribution of one of the charge elements dq of the charge distribution at the point P is given by dE, where the point P is at a distance r from this source charge element dq. Then the magnitude of this dE will be given by dq, which is the source charge of this dE, divided by 4 pi epsilon naught times the square of this distance between dq and the point P, which is our observation point. So there exists a strong analogy between this Coulomb's law and the Biot Savarts law. According to Biot Savarts law, the magnetic field, which is contributed by a small current element at any point P, distant r from that source current element, is given by mu naught over 4 pi times IDL multiplied by the unit vector r IR in the direction of this r divided by the square of the distance between this current element and our observation point P. Here, instead of the charge distribution, we are having a current distribution in form of a straight wire carrying current I. Just as we divided our charge distribution into small charge elements dq, here we will divide this current distribution into small current elements, each of length dl and carrying current I. So the current element will have a value of I times dl, that is the current carried by the element multiplied by the length of the current element. This IR over here is a unit vector in the direction of r, where r is the distance between the current element IDL and our observation point, where the contribution to the total magnetic field by this current element will be denoted by dB. So here, instead of 1 over 4 pi epsilon naught, we are having mu naught over 4 pi, and you will observe that in all the relations for dB we will have this constant mu naught divided by 4 pi, just as we had 1 over 4 pi epsilon naught in case of the electric fields. This mu naught is the permeability of free space, the magnetic permeability of the free space, just as this was the electric permittivity of the free space. So here you can see there is a strong analogy between the electric fields and the magnetic fields, or the strong analogy between the Coulomb's law applied to the electric fields to the Biot Savarts law applied to the magnetic fields. Here you can see dE, which is the contribution to the total electric field by dq, and here you can see dB, which is the contribution of this current element IDL to the total magnetic field B at this point. Similarly, 1 over 4 pi epsilon naught is replaced by mu naught over 4 pi r square. There is inverse square relationship for the electric fields. In the same way, there is inverse square relationship for the magnetic fields as well, whereas this one is the unit vector IR in the direction of R. So this equation gives us Biot Savarts law, which is applied to determine the magnitude of this magnetic field at any point P due to the current distributions. In simple words, the Biot Savarts law is applied to determine the contribution of any current element at any points in the region surrounding this current distribution. So the contribution due to the single element is dB, and the total magnetic field in this region will be obtained by integrating this equation. So we will get the magnetic field due to current distribution at any point P. This equation gives you the Biot Savarts law, or this is the mathematical statement of this Biot Savarts law, which determines the magnetic field at any point P due to current distributions. So applying Biot Savarts law, you get the magnitude of B at any point P, and to determine the direction, we will apply the right hand rule. If you hold a wire carrying current I in your right hand such that your thumb points in the direction of the current, then the curled fingers will give you the direction of the magnetic field produced by that current carrying wire. So one point which you must remember is that if the current is straight, the magnetic field around that straight current carrying wire will be in form of rings surrounding that current carrying wire. So magnetic field will be in form of circular rings. But if the current is in form of circular rings, just as over here, you can see that the current flowing in the wire is in form of circles, then the magnetic field will be in form of straight lines. So we will apply the same right hand rule, but this time we will curl our fingers of the right hand in the direction of the current. Then the straight thumb will give us the direction of the magnetic field. So the case is reversed. That is, here we curled the fingers. We stretched our thumb in the direction of the current, and the curled fingers gave us the direction of B. And here we are curling our fingers in the direction of current, and this stretched thumb is giving us the direction of B. So in that case, the curled fingers gave us the direction of B, and here the stretched thumb is giving us the direction of B. So the two cases are reversed. When the currents are in form of rings, this magnetic field will be in form of straight lines, and if the current is straight, then the magnetic field will be in form of rings. So in both cases, the right hand rule is applicable to determine the direction of magnetic field produced by the current carrying wires.